Okay, we're going to talk about couples now. And suppose we have a situation where we have two forces. They're parallel, but with opposite sense. So one force is in this direction, and one force equal magnitude is in this direction. Well, this produces a couple. Let's imagine that we have a shape that this is acting on. Then we can do is we can pick a point anywhere in this shape. Let's say here, and we'll take a perpendicular distance then. Let's do a perpendicular distance, certainly from this vector to this. And then from this vector, let's just go also in the same. Yeah. So we have distances here. So the distance from here to here, let's call this d prime, and let's call the distance from here between these two d. Then if we want to figure out the moments about some point P, say, the moment about P, what does it equal? It equals the top force times d plus d prime, because these are both 90 degrees, and then minus, well, we got it backwards. You have minus the top force because it's going clockwise sense, and then this bottom force here is going counterclockwise, so we're going to add it, and it's force times d prime. Well, as you see, then you end up with minus fd minus fd prime plus fd prime. These two cancel out, and we're left with the moment about P equals, in this case, minus d, or it just means that it's f times d in clockwise direction. Well, what if I took a point between these two? Right here. Well, this is d over 2. d over 2. So in the second case, let's call this O. The moment about O is our first force is going in the negative direction, minus F times d2. Our second force is also going negative here, F d2. These are over 2 actually. So this equals minus F. d2 plus d2 is d. So it is the exact same moment. And in fact, no matter where I take this, no matter what point I take this from, if I take it from this point here, I could extend these lines of action and do the same thing. We're going to end up with the exact same moment. So essentially, the moment here, due to a couple, equals whatever the force is times d, and it'll be in this direction. If the forces were reversed, the moment would be in the other direction. Since we can take this moment anywhere, in this space, about any point, anywhere really, this is what we call a free or a floating free moment. We can put it anywhere we want. And keep in mind, we have the right-hand rule always to guide us here. So, right-hand rule dictates that a moment rotates in this direction is positive. Now let's consider two forces that are parallel in space. Can we do the same thing about a point O? Yes, we can. So we have, say, some point O here. I can draw a vector, a position vector, to one of these forces. And then, figures, doesn't go back, huh? So, R to some point here, let's call it B, and have another point on this force vector. I'll draw two, and I'll call this RA and RB. Well, if I want to figure out the moments here, the moment about O is, if we sum our moments about O, we have NRB cross F plus the RA cross F. Now we can think of this as like minus F, and this is positive F, let's just say. So this is minus F. And really it's not necessary to consider that. We'll just call them F's. Well, this equals RB minus RA cross F, which is this vector and we can just call that R. I think I am going to leave this minus in here. Because it makes a little more sense. Now notice I can start my position vectors anywhere. I could have a different position vector down here and call it P. And this calculation is independent of the position that we are taking the moment about. Notice if I were to do that, we still end up with the moment equals R cross F. And furthermore, I could take and choose different points here, C and D. I still will have, and I can go from any point. I'm still going to end up at the same, with the same moment, because this is a free floating moment. Analogous to what happened up here. Now suppose I have multiple couple vectors here. Well, I can find a resultant couple vector, and it's just m1 plus m2. We can just do vector math on these and get that. So this means that for a resultant couple moment, you just sum R cross F's. So in the picture to the left, let's find our resulting couple moment. To start with, let's take a position vector from here to here between these two 60-pound forces. So my tail's going to start here to here. So we'll go I, J, K. K in the X direction, we're heading out 4. In the J direction, we head out 5. And then from here to here in the K direction, we're going to go down. Oops, this isn't 4 in the X direction, this is 4 at the angle down from the Y axis. It's 4 inch, it's 4 down, so we actually have to do a little bit of trigonometry here. So in the X direction, this is going to be 4 cosine 30 degrees. And then in the Z direction, it's going to be minus 4 sine of 30 degrees. Close this up. Let's space these out a little. Okay, clean that up a little bit. And then I have this vector and that's heading up 60 in the K direction. There is no X or Y components there. So that's the first couple. My second couple is going to be this determinant. Should have given myself more space. But for a position vector on this one, let's actually use a different color. And again, let's choose to start here at the negative vector. So in the X direction, I'm going positive. So let's shoot. First off, let's show you where we're going to shoot this. We'll shoot from here down to here. So I know the magnitude of that is 320 pound-inch. But let's set that up in a vector. It's going to be for the X component, or for the X component of the position vector, we're going to have 4 cosine 30 degrees. And then we're going to have 0 and then minus 4 sine of 30 degrees. I was looking here when I rewrote this, I forgot to put the minus sign back in there. And then this is going to be 0. We have 80 in the Y direction, and then 0.